is Dongxing, and I'm from the School of Education, Sanda University in Shanghai. Today, I'm excited to talk with you about the adaptive token boundaries. Or let's be simple terms, how we can make AI systems process information more like humans do. Okay, so let's move to this picture. So let me start with the big picture. Humans are remarkably good at integrating information from different scans. When you look at a photo with a caption, you effortlessly connect the words with what you are saying. You don't process the image and task separately, right? Your brain naturally links related pieces together. Current AI systems, especially multimodal image language models or multimodal LLMs, have made impressive progress in handling both images and text, but there's still a significant gap between how these systems process information and how our human brains do it. Our research focuses on closing this gap by learning from human cognition. So how do humans process information? Looking at this slide, we can see that our brains naturally organize complex information into meaningful chunks. For example, when you read a sentence, the woman watched as her dog chased after the ball in the park. Your eyes might move from the words woman to the woman in the image, from dog to the dog, and from ball to the ball. You're not seeing this as separate, disconnected elements. You are ultimately grouping related concepts across text and image. These chunks are dynamic and context sensitive. The way we group information changes depending on what we are focusing on and what task we are trying to accomplish. This chunking process helps us overcome the natural limitation of our working memory. Let's move to next slide. Okay, so how current AI models process information? As all of you in front of the screen are experts from computer or AI science. So we all know that in contrast, handle multimodal information. As you can see in this graph, they typically use fixed static tokenization schemes. Text is broken into subwords using methods like byte pair encoding. Images are divided into fixed size pitches, typically 16 times 16 pixel squares, regardless what's in the image. The key point here is that each modality, text and image, is processed separately at first, with integration happening much later in the process. This approach is quite different from how humans process information, and it creates some significant limitations. This slide directly compares human process with current AI approaches. The key differences are, first, humans use dynamic boundaries that adapt to content, while AI use static tokenization that doesn't change based on what's in the image or text. Second, human integrate information across modalities from the very beginning, while AI systems process each modality separately before integration. Third, human organize information hierarchically from broad senses down to specific details, while AI represent, representations tend to be flatter. Finally, humans are highly sensitive to content, adapting how they process information based on the situation is create real constraints on how well current AI system can understand and reason about multimodal information. So let's see this picture. So first, let's say the finger to one. So moving, we are now looking at how current AI models handle multimodal information. This diagram compares tokenization methods across several leading models like BERT, GPT, and Flamingo. As you can see in the table test, tokenization varies across models. The lower section shows examples of how task is broken into tokens like playing, with, right, red, ball. Notice that these are subword units rather than the meaningful semantic units. For images, the uniform grid pattern illustrates how images are divided into equal-sized patches, typically 16 times 16 pixels, without consideration for the actual content or a meaning within this practice. So for this whole finger, I have six sub fingers. It's all about the tokenization measures across models. I I don't think I have enough time to describe it one by one. So I just show it from the slide. So you can say, I just, for example, explain how A, finger to A works. And then you can say B, C, and also D, E, F. Okay, so let's move to next. So let's explain our research approach. To better understand this difference and developing improved approaches, we conduct several human studies. We used eye tracking to say where people look when viewing image test pairs. This helps us understand how attention moves between related elements. We use the functional MRI to observe brain activity during multimodal processing, showing regions activate and how they communicate. And we conducted working memory tests to people can remember at once. These studies give valuable insights into human multimodal processing that we could then apply to a system. So Here's some key findings from our human studies. The heat map shows how people quickly shift attention between related elements across modalities. One test mentioned specific objects. Participants moved their eyes to the corresponding regions in the image within about 2.67 milliseconds. The brain network illustration shows synchronized activity between visual processing regions and the language areas. This indicates integrated rather than separate processing. And our working memory assessment found that people can effectively remember about 4 to 6 cross-modal chunks, regardless of how many individual elements are contained in each chunk. Performance drops sharply when the number of distinct units exceeds this capability. These findings align with established chunking theories when extending them to the multimodal domain. So let's say this. So from figure one, we show some evidence of cross-modal chunking in human cognition. Okay, so let me walk you through figure 1A, which shows evidence of cross-modal chunking in human cognition. What you are seeing here is a visualization of eye tracking data from our human studies. The red oval areas represent fixation density, basically where people spend time looking at the image. The blue dotted lines show the scan path, how people's eye moved from one point to another. Notice how these fixations directly align with the task shown at the bottom. When the participants read the woman watched as her dog chased after the ball in the park, their gaze immediately shifted to the corresponding elements in the image. You can see concentrated attention on the woman, the dog, and the ball mentioned in the text. And then let's move to 1B. So figure 1B shows the natural basis of this cross-modal chunking. On the left side, you can see the connectly matrix between different brain regions. The fuse inform guides FG, little optical complex SOC, superceptual locus STS, and the broadcast area. The color intensity represents the stress of function connectivity between these regions. Okay, so yeah, because of time, I don't have enough time to explain all the details. So let's move to slide 8. So our solution, what's our solution? Our solution is based on this insights, we developed what we call the dynamic cross-modal tokenization framework, or DCMT. This approach intends the standards transformer architecture with 3 main components that you can see on the screen. First, adaptive token boundaries that respond to content and context rather than using fixed tokenization. This is very important. I think it's also the chain of the AI development. And second, hierarchical representations across multiple levels from broad schemes down to specific features. And third, cross-modal alignment mechanisms that actually connect related information across modalities. Let me explain each of these components in more details. Okay, so first, let's say the adaptive token boundaries. Traditional approaches use fixed tokenization schemes like dividing every image into same grades of patches regardless of content. You can see this on the left side of the slide. Our approach shown on the right implements differentiable boundary detectors that optimize token segmentation based on the content itself. The system learns to identify meaningful units rather than use arbitrary divisions. This is more like how humans process information. We naturally focus on meaningful objects and their relationships rather than processing every pixel equally. And then let's say this. When we see hierarchical representations, the second component of our framework involves hierarchical token structures, as you can see in this tree-like virtualization. We implemented multi-level transformer encoders operating at different semantic scales. At the top level, we might have a scheme representation like kitchen activity. At the middle level, we have the entities like person cooking and objects. And at the lower level, we have specific features and parts like faces, hands, bowls, and food items. Importantly, there are bidirectional connections enabling information flow between levels. This allows the system to reason about relationships between different levels of abstraction, similar to how human can flexibility shift the focus from the big picture to specific details. And then let's say this. So this is about the cross-modal alignment. The third component focus on actively aligning information across modal activities. As you can see in this visualization, we incorporated contrastive learning objectives and mutual information estimators that promote correspondence between virtual and linguistic tokens. This creates explicit connections between related elements, like linking the word dog with the virtual representation of a dog in the image. This alignment mechanism operates multiple levels of the hierarchy, allowing for rich cross-modal associations. Together, these three components create a framework that much more closely resembles human information processing. Okay, I think I don't have enough time to explain for finger three actually about the dynamic cross-modal tokenization framework. So let's just move to our research, our results. Okay, so how well does our approach work? This chart shows the performance comparison of our DCMT framework alignment, state-of-the-art models like BLIP, Flamingo, and GPT-4 across several benchmark tasks. As you can see, approach demonstrated significant improvements across all benchmarks. On visual question answering, we achieved a 7.7 7.8. In description, we saw a 5.3% improvement. Most notably, on our specialized cross-modal trunking evaluation dataset, specially designed to test the integration capabilities, we observed a substantial 13.7% improvement compared to GPT-4 So this quantitative results demonstrate that our approach not only has the theoretical interest, but also delivers practical performance benefits. Okay, then let's move to the beyond raw performance numbers. We also analyze how our models behavior compared to human cognitive patterns. These four piles show different aspects of this comparison. The attention pile shows that our DCMT models' attention patterns lie much more closely with human gaze distribution than baseline models. The correlation with human attention was 0.68 for a model, whereas 0.41 for baseline approaches. The air patterns panel shows that our model makes similar types of mistakes as humans, particularly in case require integration of multiple information elements. The content sensitivity panel demonstrates that our model adapts to content contextual factors in a human-like way, adjusting token representations based on task demands and semantic relationships. And the transfer learning panel shows that when it evaluated on novel tasks not encountered during training, our model showed superior generalization capabilities, with much less performance drop-off compared to baseline models. This result suggests that our approach is not just performing better on benchmarks, but is actually processing information in a more human-like way. And so for this figure 4, if you have interest, you can say from my paper, I don't to describe it in detail. And then let's say why this matters. Why does all this matter? These are both theoretical and practical implications of our work. From a theoretical perspective, our research helps bridge the gap between cognitive science and AI. It suggests that incorporating cognitive constraints and processing mechanisms observed in the human can provide useful inductive bias for AI systems. Our findings also highlight that the importance of representational structures in addition to architectural innovations, while attention mechanisms have been the primary focus of recent research. Our results indicate that the fundamental units of representation tokens play an equally critical role. From a practical perspective, AI systems that process information more like humans do can enable more natural human AI interactions. They can lead to better education technology that aligns with how students learn. They can improve assisted assisting systems for people with disabilities, and they can facilitate more intuitive AI reasoning that humans can better understand and trust. Of course, our current approach has several limitations that are important to acknowledge. The computational demands of dynamic tokenization present practical challenges for deployment in resource constrained environment, while our optimization techniques reduce the memory requirements significantly. Further efficiency improvements will be necessary. Our human studies were conducted with, were conducted with a relatively small sample size, particularly for the neuroimaging component, which may limit the generalizability of our findings. And our evaluation focused primarily on visual-linguistic integration, with additional research need to determine whether similar principles apply to other modality combinations. Looking to the future, we are interested in extending the dynamic tokenization framework to incorporate temporal dynamics, which would better capture the sequential nature of human information processing. We're also exploring the neuromorphic approaches that more directly simulate neutral security, which might provide future insight into effective cross-modal integration. Okay, I think it's almost my time. Let me make my conclusion. So our research has demonstrated that bridging the gap between human cross-modal trunking and the token representation in multimodal LLMs yields significant benefits. Human cognition offers valuable inspiration for improving AI systems. The dynamic, context-sensitive nature of human trunking represents a crucial capability that conventional AI systems had yet to fully replicate. By incorporating dynamic, hierarchical, and aligned token representations, our DCMT framework achieves both improved task performance and greater cognitive plausibility. As multimodal AI systems become increasingly integrated into various aspects of human activity, ensuring their capability with human cognitive patterns will be essential for effective collaboration and communication. Okay, thank you